Okay, guys, let's go ahead and jump into IP addressing. So this is going to be domain 1.7. Given a scenario, use appropriate IPv4 network addressing. So it wants us to start off just jumping right into it and saying, hey, go over public versus private and the different IP types and then start subnetting. So I don't really like the way I don't even know if they made it this way on purpose. They're just saying go over this and then you figure out how to teach it. But I'm going to do this in order. I'm going to go over what an IP address is, what it's used for, go over binary, the machine language, 1 bits, 0 bits, on bits versus off bits. Once we go over that, the structure of IP addressing, we'll jump into subnetting. This is going to be a quick down and dirty of subnetting. So what is a variable length subnet mask? We're going to go into CIDR. This is easy, though. This is just us going over the slashes. What do the slashes mean, right? And then once we do that, we'll finish up by going over public versus private and then the different classes. Now, this is really old school, like the IP4 address classes. We don't really do classful addressing anymore, but we'll go over their ranges. That's what I need you to know. Just the ranges in these classes. So first, IP4 overview. So what is it? Why do we need it? So for devices, computers, nodes on a computer network, they need a unique address to be able to communicate to each other across the internet, in their LANs, and WANs, anywhere. You need an address. So we use something called the Internet Protocol, version 4. There is a version 6, but here we're going over version 4. So IPv4 is the standard protocol we use to have our devices communicate over our networks, whatever that network may be, your internal small office, your LAN, or on the internet. So for devices to communicate across the internet, they all need a standard protocol to deliver traffic. In today's world, that is the Internet Protocol. IPv4 is also going to be hierarchical in its nature and its structure, which we'll get into. So IPv4 addresses at the machine language, the computer language, they're going to be 32 bits. So what is a bit? A bit is a 1 or 0, and that is binary, right? So when we talk about binary, that is the computer language. So binary bits. That is either a 1, which equals an on bit, or a 0, which equals an off bit. And that is how computers communicate. Now, this is not a Computer Science 101 class, so again, I can't spend a week talking about this, but that's what it is. An IPv4 address is 32 bits. We then structure those 32 bits into 4 different octets, which contain 8 bits, or a byte, a single byte. So let's break that down again. So if I'm looking at an IPv4 address as a computer, here's how I read it. I just read it like, let me get this out. I read it like this: 100100001, 1000001. What is that? Is that 8? 1. Then 100010001. That's 8, I think. And then I'm just going to make this easy on myself. So that's how a computer reads it. Just a single string of 32 bits makes up an IP address. Now, us as humans, how to reread it? Well, what we do is we break it up just like I did. We take the 32 bits and split them up into 4 separate octets here. 8 bits in each octet. So each octet is also a single byte, okay? So you can also say it as 4 bytes. And yes, I'm being very careful with the language because on the exam, they could say 32-bit address, 4-byte address, an IPv4 address. How many bits are in an octet? You'll need to know this. So each one of these is an octet. Now we take these octets, these 8 bits, and we convert them into what's called dotted decimal format, which to you, that's just a regular number. So we convert that octet into dotted decimal, which is just a number 0 through 255. Now I'm going to teach you how we convert ones and zeros into real-world numbers like this. It's going to be from right to left, it empowers a 2. We'll get into that when we get into our binary conversion chart. Okay? So an IPv4 address is 32 bits, separated into 4 octets, 8 bits each. We convert that into what's called dotted decimal format, which is what you're used to seeing. That's this 192.168.0.65. That's an IPv4 address. Now, we have to go over how we do those conversions. How do we convert 8 bits into a number? And why is it 0 through 255? Because in binary, when we're converting, we go in powers of 2. We're going to get into that, okay? And it'll be right to left. Let's go to our next slide. Oh, no. Okay, cool. So now I'm going to bring up a whiteboard. Now let's get into this, okay? Let me bring up whiteboard here. All right. So in this whiteboard, let me get this epic pen out of the way. We're going to be going over IPv4 conversions. So how do we convert from binary into dotted decimal? So let's check this out. So first, we're going to start by going from binary to dotted decimal. So I'm going to write some things up here. A 1 bit equals on. Then a 0 bit equals off. Okay? So a 1 bit equals on, and a 0 bit equals off. Now IPv4 addresses. They are 32 bits in length, correct? Yes, they are. So an IPv4 address equals 32 bits. So if I want to convert this binary, let's write it out, 000111100.111.000.10101010. I know it's a lot. Did I do too many there? 10.000.0011. How do we do this? So we're going to have to calculate all the on bits under what I call a binary conversion chart. So that binary conversion chart is going to look like this. It's going to be 128. Let me make this a little bigger. 128, 64, 32, 16, 8, 4, 2, and 1. That's our binary conversion chart. Now, what do you notice up here? There's 8 digits here. So remember I said binary? It goes in powers of 2. So this first bit here is going to be in powers of 2. And we have 8 bits here. So that'll be 2 to the 8th power. That equals 256. But it doubles each time to equal that, okay? So it's literally just 2 times 2 times 2 times 2, 16 times 2, 32, right, times 2, and then 64 times 2, 128. And that'll equal 256, okay? So that's how we do our binary conversion. Now, our main goal is I want to convert this. So I want to convert this 32-bit address to what I call dotted decimal. Now, what I call, that's what the industry calls it, right? That's our correct term, dotted decimal. So we want to convert to dotted decimal. So what I'm going to do is I'm going to take this octet, and I'm going to put it under my binary conversion chart. So this right here, remember, is called a binary conversion chart. The binary conversion chart. So here's how we do it. From left to right, we're going to put our bits underneath here. 0 bit, 0 bit, 0 bit, and 1, 1, 1, 0 bit, 0 bit. So since 0 bits are off, this is going to equal 0. This will equal 0. This equals 0. But 1 bit's equal on, which means this is going to be 16, 8, and 4. We have to add those up. This is 0. This is 0. We add up our 1 bits, and that's going to give us our number. So 16 plus 8 is 24. 24 plus 4 is 28. So our first octet here is 28. That's how we convert to dotted decimal. Now I'm going to finish this. And again, I'm sorry guys, but I'm only going to do this one time because I don't want to spend our whole afternoon just doing this because as you can tell, it's kind of a slow burn, right? Okay, so our next octet. Let's do it. So we're only going to care about the on bits here. So 128 plus 64 plus 32 plus 16. That is 240. So here's this guy. Our next octet. Let's do it. Is going to be 1, 0, 1, 0, 1, 0, 1, 0. Okay, made it difficult on myself. So that's going to be 128 plus 32. We're only counting the on bits. Plus 8 plus 2. So let's see. 8 plus 32 is 40. Plus 2 is 42. 42 plus 128 is 170. So I just did some quick math, okay, in my head. And then last octet here. I made it easy on myself. Then just 1, 1. So these are all off bits, so we don't need to count them. And remember, we're converting from binary to dotted decimal, what an actual IP address looks like. You know, that's going to equal 3, right? Because that's 2 plus 1, so dot 3. And we just converted that successfully on our own. No calculators, like some real computers. All right, now let's do it the opposite way. Now, instead of converting from binary to dotted decimal, let's convert from dotted decimal to binary. This is the important one because this is going to be what we need to know when we start subnetting, okay? So what I'm going to do here is just scroll down. Actually, I'm going to grab my binary conversion chart. Okay. Let's scroll down. There's my binary conversion chart. I don't need this little bar above it anymore. Okay. Now let's convert this. Let's go ahead and convert 192.168.0.1. So we're going to convert this dotted decimal into binary. So now we're going to do the opposite of what we just did. We're going to go from dotted decimal into binary. So how do we do this? So we do it per octet. So first we got to convert this octet here into 8 bits from our real whole number, dotted decimal, into binary. So here's how we do it, guys. What we're going to do is we're going to take that number and we're going to put it above our binary conversion chart. And here's what we're going to say. Is our original number, 192, bigger than or greater to 128? And if it is, that's going to be an on bit. And before we move on, if our original number is greater than or equal to, we're going to do some subtraction. So now we're taking away 128 from 192. So, math in public, don't judge me. What is 192 minus 128? 64. I should have known that. My goodness. Okay, I've been doing network engineering long enough. Okay, moving on. So 192 is greater than or equal to 128. So then we do our subtraction. That equals 64. Now, is 64 greater than or equal to 64? Well, it's equal to. So guess what that is? An on bit, a 1 bit. And then 64 minus 64 is 0. And then if we ask that same question down the line, is 0 greater than or equal to any of these numbers? What's our answer? No. 0 is not greater than or equal to any of these numbers. So the rest are going to be off bits, zeros. So this first octet here is 1, 1, and then the rest are zeros. Now, let's convert 168. Let's do it. So we're going to ask the same exact question and do the same exact thing. Is 168 greater than or equal to 128? Yes, it is. That's an on bit. So 168 minus 128. I'm using my calculator again, sorry. Had a long day today, afternoon class. I'm sure you guys can understand. 168 minus 128 is 40. Okay. So then we get 40. Is 40 greater than or equal to 64? It's not. It's less than. So guess what? Off bit. Is 40 greater than or equal to 32? It's greater than. So guess what? On bit. What about 8 to 16? 8 is not greater or equal to 16. Off bit. Now is 8 greater than or equal to 8? Okay. Easy. On bit. And then the rest is zeros. And there we go. So 168 converts to 1, 0, 1, 0, 1, 0, 0, 0. I'm going to save you some time here. If the number is 0, it's less than all these. So that's all zeros in binary. And then the number 1, I will put this up on the chart, even though hopefully if you're able to follow along. I know this is quite boring. But it's the fundamentals, right? The fundamentals aren't always sexy, It ain't always fun. 1 is not greater than anything, but it's equal to 1. So that'd be our only on bit. And there you go. That's how we do those conversions, okay? All right. Now let's take a little quick breather. I'm going to take a quick breather. And you just learned about IP addressing. So that's how an IP address is structured. You learned how to convert from binary to dotted decimal, from dotted decimal to binary. Pretty much you use this binary conversion chart here. That's the most important thing. Now, IP addresses belong to networks, right? So I'm going to give us all a breather while I draw out a network here. So let me... Okay. So I'm going to draw out a network here. Because in the real world, just knowing how to do that really doesn't help you when you're doing subnetting, you're setting up networks, and you're doing that variable length subnet mask, okay? So let's say I have a router here, and this is our Houston office. I think that's how you do Houston. And then we have a switch down here. And then we have our little office, so we have some printers, some VoIP phones. Connected are some laptops. We have a little access point. And that access point, actually I don't want to draw it like that. I'll draw it like this. Has little Wi-Fi enabled devices connected to it. iPhone. So we have our network down here, okay? But we know that every single device on here needs an IP address. So we say, hey, this Houston network, this local area network here, is 192.168.0.0/24. So now we have to break this down. Here's where subnetting comes into play. Here's where we start understanding what this CIDR actually means. Okay, those are zeros. And how this defines a network. Because with IPv4 addressing, so remember I said it goes in powers of 2. So when we have an 8-bit octet, so we have 8 bits here in our octet, the total value of 8 bits is equal to what? 256. Because there's 8 bits here, so 2 to the power of 8, right? But an IP address is what? 32 bits. So if I do 2 to the power of 32 through my calculator, how do I get like my advanced scientific? There we go. If I do 2 to the power of 32, whatever that long number is, that's how many possible IP addresses I can have. 4.2 billion, okay? Now let's look at the history of the internet. When the internet first started, it was called DARPANET, and they created the internet. And then when the TCP IP model became the standard, there was literally like 6 routers in the world, right? Now, I don't know the exact number. I'm being exaggerating, but there wasn't a lot of people. So all those like routers probably had like, they're all like this part of the same network, or maybe they had 5 or 6 different networks. And then as the internet started sprouting, we said, holy crap, we need to start breaking down our total amount of IPv4 addresses available into different subnets. So then we started coming up with classful addressing, where we had /8, /16, /24, and this subnet mask actually represented the inverse, where it said, hey, this /24 actually means you have 8 bits left over to make your host. So a /24 actually says, hey, out of the 32 bits in IPv4 addressing period, this network here, 192.168.0.0, out of the 32 bits, 24 of those bits are not going to be usable. You're going to have 8 bits left over, equaling 256 for unique IP addressing, okay? So let's break this down. So this /24. This /24, if we convert that into a subnet mask, a /24 actually equals 11111111.11111111, and then the rest is zeros. Okay, so here's where we got to put our thinking caps on. So a /24 essentially means we have 24 1-bits here. In subnetting, when we look at a subnet mask, okay, the 1-bits equal our network. It defines our network, okay? And then the 0 bits equal the number of hosts we can have. The number of hosts we can have, okay? Now, stay with me. I know might be a little boring. So if I convert, so /24 means we have 24 network bits. So if I convert this to dotted decimal, that's 255.255.255.0. And then these zeros here represent the number of hosts. So you're going to look at me and say, well, they're zeros, so doesn't that mean 0? Well, that's not how subnetting works. In subnetting, zeros represent the number of hosts you can have. So what we mean by that is that if I put my binary conversion chart back up on here, 28, 64, 32, 16, 8, 4, 2, and 1, and I put all the zeros up here, guess what? That equals what? So forget what we learned about in that binary conversion chart. That's still accurate when we're converting IP to dotted decimal to binary and whatnot. But if I were to add up all these numbers, that's 256. So a /24 means you have 256 IP addresses available. All right. Now let's say, so before I move on, that means this 192.168.0 network has .0 to .255 of available IP addresses to use, okay? So now down here, so on this router, we would make this interface like .1. That means all these users here can have an IP address after .1, okay? And that's going to be the unique IP. And they all know that they're in each other's networks because guess what? Every single device here is going to get an IP address like 192.168.0.5. This will be .10. And they're also going to have a subnet mask associated with them. And they're going to be like, oh yeah, I know my network limits are 0 through 255, so I know .0.10 is in my network because of my subnet mask here. All right, now let's look at this. Now let's say we had this. Cut this off a little bit. 192.168.0.0/32. Sorry, /27. So /27. If I convert that CIDR into binary, that's going to be 1111, 1111, 1111. That's 24 ones. Remember, this CIDR notation represents how many network bits you have. So this is 25, 26, 27. 27 network bits. And then this is my subnet mask only. And then the rest are host bits. So what's my subnet mask going to be in dotted decimal? 255.255. Dot what? Well, guess what we have to do now? We got to come back up here to our binary conversion chart, and we got to say this last octet here, all the zeros are the host. So this is the number of hosts we can have. So we'd add all this up. So 16 plus 8 is 24, plus 4, 28, plus 2, 30, and then 31. And then 0 always counts as 1 in binary, so it's really 32. But we look at this and say, so these 1s over here. So my subnet mask would be, adding all these up, would be .224. 128 plus 64 is 192, plus 32 is 224. And then the rest of these zeros here represent how many IP addresses I can have in this network. So a /27, we have 32 IPs available in there. So now if I did this, made this a /27 instead, remember this is just something you configure. Like I come on the router and I make it a /27 and I make these all a /27. Now it's .0 to .31 because 0 counts as 1 here. That's my network. So if I have this computer, I have this printer, they're /27s, and they have their unique IP addresses in here, okay? But then let's say this phone over here is 192.168.0.40/27. What's going to be the issue here? Remember, this is defining our network range. This is defining our network limits. So this PC is .5, this printer is .10. They're both /27. So they know, yeah, we're within that range. You know, I'm .5, you're .10. We're within that range of 0 to 31. But this phone over here is .40. That's outside our network. So guess what? That's outside our network range here. They're not part of our network at all. This is a whole new network over here. That's the beauty of subnetting. And then we tie these subnets into different VLAN tags, and then we start segmenting our network, okay? All right. Let's go ahead and take another 10-minute break. Let's come back at 6:30, and then we're going to jump right into how I break down subnetting, okay? Yeah, so let's come back at 6:30, and we're going to break down subnetting. And I'm only going to spend like 20 minutes on it. Then we have to move on because I just want to get through some stuff today. So yeah, come back in 10 minutes. Okay, now let's go over how I actually will subnet, like real world. Okay, so let's say we have this scenario, guys. Let's say we have actually the Trepa Corporation. Trepa Corporation. We have this router here, that's our HQ router. And our HQ router is connected to Office 1. And this router is connected to Office 2. Now, let's say in this made-up scenario, because if you already know what private IP addresses are, you know we wouldn't have to do this, but this is kind of how testing and when you learn the fundamentals, how they want you to do it. Let's say we have to subnet from a /24. So we have 10.0.0.0/24. And let's say at HQ, we have 48 users, 48 hosts, however you want to call it, because, right, we'll do 48 hosts, probably more accurate, because we could have a printer. It's not a user, but it needs an IP. Office 2, we have 25 hosts. And Office 1, we got 16 hosts. So now from this /24, we need to break this down into a subnet that fits this 48, a subnet that fits this 25, and this 16. This is what we would call like variable length subnet mask, okay? So from this /24, breaking it down into smaller subnets. So how do we do this? So I have my steps over here. These steps are like how I've been teaching subnetting since 2017. And it always works. If you can remember these steps, you'll always know how to subnet. So our first step, convert the number of hosts to binary. So again, the Trepa Corporation, we have a /24 that we want to break down here, okay? And so we have this subnet, this subnet, and this subnet. Now I know this point-to-point connections will also be a subnet as well. We'll put those as /31. We'll do those at the end. So we're breaking down really 5 subnets from our original subnet here, /24. Okay, so step 1, convert the number of hosts to binary. So when we're subnetting, we always start at our largest host requirement. So we have 48 users. So we got to convert the number of hosts to binary. So I have 48 hosts here. So really when I say convert the number of hosts to binary, this is also asking how many bits does it take to meet your host requirement. So how many bits does it take to meet your host requirement? So we have 48 hosts. So how would I figure out how many bits will it take to get the number 48? Well, for that, we need our binary conversion chart. So let's draw up our binary conversion chart here. Okay, so 48. Let's convert it to binary. Do you remember how to do that? 48, is it greater than or equal to 128? No. 48, is it greater or equal to 64? No. Is it greater or equal to than 32? Yes. So we can stop right here. We can stop right here. So the rest of this, like this is going to equal 16, right? And then we'll have a 1 here, and then the rest will be zeros. So this will be 16. And then, so how many bits did it take to get the number 48? So you may say, oh, I see a lot of my students, like it only took 2 bits. You think it's just these ones here. But that's wrong. It actually took us 6 bits. Because if we actually look at this, like if I were to just quickly erase all this nonsense, this is the binary. This is how we get the number 48. It's 110000. That's how we get the number 48. It takes these 6 bits to get to number 48. So it takes 6 bits. So that fulfills step 1. How many bits does it take to meet your host requirement? I'm going to write this back up here, our binary conversion chart, because we will need it. Okay, step 2. Convert your CIDR or subnet mask into binary. Now I'm going to put in here, convert your original CIDR or subnet mask into binary. So our original subnet mask is a /24. So what is that in binary? And then all zeros. So that's easy. That's our original subnet. Now step 3, reserve the bits in the mask. So really what we're saying here is convert from, well, we'll save that. So reserve the bits in the mask. So how many bits did it take to meet our host requirement of 48? It took 6. So that means from right to left, it took us 6 bits. So that is going to be this. Remember, it took us 6 bits. So in our last octet here, from right to left, we need 6 host bits. So that means the rest of these convert to 1s. So reserve the bits in the mask. I'm going to put reserve the host bits. Reserve the host bits in the mask from right to left. Now remember, it's very key here to remember that host bits and subnetting are zeros. So this is our new subnet here. So right here is our new subnet. And if we convert this to dotted decimal, one and 1, put that back up on our binary conversion chart here. That's going to be .192. So this is our new subnet mask. 255.255.255.192. And our CIDR notation, remember that's that slash. That CIDR notation represents how many 1 bits, how many network bits you have in a subnet mask. So we have 8, 16, 24, 25, 26. So that is /26. Okay? Now we're not done yet. So remember, this is our new subnet for HQ. So now step 4 is find your increment and network range. So now what we're pretty much saying here is, hey, cool, I have a /26. Here's my new subnet mask. But what's my network range? So we're starting at 10.0.0.0. So this last network bit here and your subnet mask, the last network bit here, is going to be your increment. So that's 64. So our increment equals 64. And our network range is going to be this, 10.0.0.0 through .63. So we pretty much just add that. And you may say, well, 0 plus 64 is 64. But remember, in computer networks, 0 always counts as 1. Okay? So that's our new network range. So at the HQ network, it's going to be 10.0.0.0/26. And so we have 64 IP addresses. And this is our usable range here. All right? Now I'm going to do this one more time. 2 more times for Office 2 and Office 1, and then we have to move on. I'm recording this, so if you have any questions, you can go back and watch. I also have multiple videos online and in our LMS that go through this same process over and over, okay? So we figured out our first network here for HQ. Now we're going to redo this entire process. And we're going to go on to our next highest host requirement, which is 25 hosts here. So, how many bits does it take to get to the number 25? So let's do our let's convert 25 to binary. 0, 0, 0. And then 25 is greater than 16. So that's 1. And at this point, we can stop. Because now we know it doesn't matter what comes after this. right? It's going to be 001. It's going to take 5 bits. No matter what, once we get that first on bit here in our conversion in step 1, that's how many bits it's going to take. So we got our first 1 bit here. We know we need 4 more after that, so a total of 5 bits. Now we're going to convert your original CIDR or subnet mask into binary. So our original subnet mask is /24. I know this is repetitive, but do this every time. Next, we're going to reserve the host bits in the mask from right to left. So how many bits did we need to meet our host requirement? We needed 5. So that means we need 5 host bits. Host bits in subnetting are the zeros. And the rest become network bits. So our new subnet mask would be this. Remember, we reserved 5 host bits. That's how many bits we need to equal the number 25. So here's our new subnet mask. So these 1 bits, right, we put them back up on our chart. 1, 1, 1, 1. That equals .224. So our new subnet mask is what? 255.255.255.224. And what's our CIDR notation? Remember, the slash, that CIDR notation, is how many network bits we have in our new subnet mask. So that's 8, 16, 24, 25, 26, 27. Next, we need to find our increment. So our increment for this new subnet we're making here at Office 2, we go off our last network bit. So our increment is 32, and that's going to equal our network range. So our new network. Now remember, we already set this aside for the HQ. So we're going to start at .64, the next IP. 64 plus 32 is .95. That's in subnetting, right? And it's a /27. So there's our new network range, our new subnet for Office 2. So our new network is 10.0.64/27. Okay. We're going to do this one more time for Office 1. Alrighty, I'm going to leave this here. So Office 1 has 16 hosts. So we need to find out how many bits it's going to take to get to 16 hosts. So we start right here. 16 is greater than or equal to 16. So that's 1. We can stop right there. How many bits is it going to take to get to the number 16? It takes 5 bits. Next, we're going to take our original CIDR, our original subnet mask, converted into binary. /24 means 24 network bits, 24 ones, the rest are zeros. Next, we're going to reserve the host bits in the mask from right to left. So I need 5 bits to get to my host requirement of 16. So that's, right, 5 host bits. So then the rest are going to be ones. And then I leave my host bits there. My new subnet mask is 255.255.255.224. And then the CIDR notation, or the slash notation, is how many network bits we have. So that's 8, 16, 24. Oh, I'm missing one in there. Hold on. 24, 25, 26, 27. /27. Now, our last network bit and our subnet mask, the last one, I line that up to my chart. That's my increment. So my increment equals 32. So my new subnet for Office 1 is .96 plus 32. That is .127/27. And that's how I do subnetting. In the Google Drive, I'll upload a subnetting chart for you guys. But if you can memorize these steps, this is how I learned back when I was like a junior. I was from the help desk to junior network admin. This is how I learned it. It's actually a technique from someone called Jeremy Chara. He was a CBT Nuggets trainer. So a lot of people actually learn to subnet this way. But if you can memorize this, you'll always be good to go. Now we're almost done with IP addressing. I know I told you it was going to be a long thing because it just is. Now we have to go over public versus private, but I also want to go over with you what a default gateway is and the broadcast address. Okay. So if I had to draw out, I know we're just like you're probably like holy shit, like that was a lot, man. Now we're just moving on. We have to. Okay. So, here we go. This network here, actually, no VLAN shit yet. Okay. So I have this little network design here. At R1, at this interface here, it's going to be 192.168.0.1. And this network here is going to be 192.168.0.0/24. So right here at the router, this is going to be called our default gateway. Okay? Our default gateway. So you're always going to have to use an IP address as your default gateway. The very first IP in your network is called your network ID. This is an IP address, the .0 here, that can never be assigned. So a /24. A /24, the network range is .0 to .255. This last IP address, the very last IP address, is called the broadcast IP. That can also not be assigned. So, when I have this 192.168.0.0/24, .0 is the network ID. .1 is typically your default gateway. It doesn't have to be though, okay? And then .1 through .254, this is your usable range. So this is the range that you can assign to users. So this computer could be .254, okay? And then .255 is your broadcast IP, which cannot be assigned. So I'm going to put little red things right here. So this equals can't be assigned. And that's for every single subnet. So if I were to do that over here, if I had 192.168.0.64/27, so that range is .64 to .95. So guess what? In here, .64 is our network ID, which cannot be assigned. .65 typically would be your default gateway. Now, any IP address in the range will be your default gateway, but for most of 95% of the networks I've been on, the first usable IP will be your default gateway. That's not always the case. I have worked on a network where they made the last usable IP the default gateway. But anyways, I thought that was silly. I don't know why. Usable range. And then .95. That equals the broadcast IP. That cannot be assigned. So every single IPv4 subnet has this structure where the very first IP is a network ID, and then the first usable to the last usable, and then the last IP is the broadcast IP, which also cannot be assigned to any device in here. Okay? Alrighty. Now, I'm going to go back to the slides for the rest of this. Yeah. Actually, yeah, I'll go back to the slides. Okay. Now, again, guys, I did that quick because I don't want to spend like usually in my in-person class, when we like go 9 to 5, usually we'll spend like 2 to 3 hours on subnetting, and I'll give you diagrams to subnet from. I'll put those diagrams on the Google Drive, and then you can do it on a piece of paper. These steps that I have up here. This whiteboard, I'm also gonna email to you guys. Whiteboard's gonna be saved and can be sent as a PDF and a PNG file. But I forgot to make that group chat between you guys, so I'll make that right after this. And then I'll send out all that information for submitting. We also have videos on the LMS as well, so if this was like, holy fuck, dude, you went too quick and confused the hell out of me, like, you can go over this again, all right? Okay, so that is the fundamentals of IP addressing. Now let's go to the slides. Okay, so that was IPv4 overview. One slide took us almost an hour. All right, now we're going to go public versus private IP. So check this out, guys. So remember we did 2 to the 32nd power, 2 to the power of 32, and we came up with like 4.2 billion, and that's how many unique IP addresses there are in the world. Well, guess what? Back in like the mid-90s, like when the internet was starting to boom, the powers to be, which is like IANA, ICANN, these huge international organizations that register the IP addresses, because every single IP address back then used to be public. So like your computer could have been reached by some random dude on the internet, right? Well, we started to notice that we were going to run out. We were going to run out of unique IP addresses. So they came up with something called classful and classless addressing, and then their final solution was something called private IPs, where they used a technology called network address translation and set aside 3 different classes of IP address spaces to be used as private IPs that can never be directly connected to the internet. So let's break this down, okay? So again, this came about because we were going to run out of IP addressing, unique IP addresses. So we came up with something called RFC 1918, which is private IPs. These private IPs were IP address classes or ranges that can never be routable on the internet, that can be used between organizations with, duplicates. We could have like the office next door to me more than likely is using the same private IPs that I am on my computers, right? So how does this work? And let's define this a little bit. So remember, public versus private. So we're running out of IP address spaces, so they made private IP address ranges. You can see that IANA did that. So private IP addresses, these ranges, that you'll need to know this, they split them up into 3 different ranges. A class A range, which is 10.0.0.0/8, which pretty much is 10.0.0.0 through 10.255.255.255. They came up with a class B range, which is 172.16.0.0/12, which is .31.255. That's the range, right? And then class C. .0.0/16, which pretty much was 255.255. So I guarantee if you go to wherever your network settings are on your workstation that you're listening to me on, I'm on a MacBook, so I'm not going to do ipconfig. If you're like, just do ipconfig on command prompt. No command prompt here. When we come to details, look it. That's my private IP, right? So we all use them. So you may say, you're telling me that those IP addresses are not routable on the internet. But you're connected on the internet right now. How is that possible? You're connecting to a Zoom server that's allowing us to do this class. True. What happens is, at our routing device, whether that's a firewall, multi-layer switch, or a router, our inside network is all private IPs. So that's all of our users. This outside interface here, connected to the ISP. So I have Spectrum. So my outside interface connected to my ISP gets assigned a public IP address. And right here at this router, what we're going to do is something called NAT. Which is Network address translation. It's called NAT. And what that's going to do is it's going to convert those private IPs to a public IP, and that's how you're routing out on the internet. So if you open up Google Chrome web browser, or doesn't matter, you can open up a web browser, and you actually type in what is my public IP, there it is. So it shows like, yeah, you're not hitting the internet with that private IP address that's assigned to your computer. We're doing NAT at the router, and we're converting you to a public IP, okay? So, important to note, these private IP address ranges, a public IP is routable on the internet. These private IPs are, like it says, privacy. It's private, so you get, like, you can't directly connect to private IP addresses. And that device, that router, that's connecting you off to the internet is doing something called NAT. Okay. So here's the chart again. So private IP addresses are not routable on the global internet. They're just used for communication in your LANs, right? There's the ranges, and these ranges are reserved exclusively. Like even at this ISP, there's a router in here somewhere that's connected to your router. They'll have an access list that's just denying private IPs, right? So, okay. An APIPA address. This is called an automatic private IP addressing. This is a feature of Microsoft Windows machines that when your DHCP server runs out of space or when that computer cannot reach a DHCP server, it's going to assign itself its own IP. That range is 169.254.00 to 169.254.255.255. Okay, obviously I just put the usable range in here, but it's 00 to 255.255. So that is a Windows feature. So if you go on a workstation, like user puts in a help desk ticket, you go there, IP config, you're like, oh, 169, so you're not reaching DHCP, something's wrong, okay? A loopback / localhost. So the loopback address is something that's assigned to your NIC. It's just for like internal testing. When you like deploy a little web browser, not a web browser. When you build a website on ChatGPT and you put it in code and it's like, oh, it's at the local host, that's what that is. 127.001. That also cannot be assigned. That's not routable on the internet anywhere. No server has that IP addresses. That's something that's designated, like in the white papers in IANA, that says, hey, this can only be used on your local NIC, and that's it, just on your local device. Okay, subnetting. We already went through this, so I'm not going to get too much into it. This is just a chart of what I was explaining, how your CIDR, like /27 means you have 27 network bits or 27 ones here. I have this nice little chart as another way to look at it. And then we have the IPv4 address classes. So we have class A, which is the first octet ranges from 1 to 126. Now we don't, okay, the class B, I'm not going to, that's fine, it's just for the exam. Class B will be the first octet is 128 to 191. So if you see an IP address that says 128.0.1.1, that's technically a class B. I got to, like that example here, right? That's in that range where the first octet, we're looking at the first octet, is between 128 and 191. A class C is that first octet is 192 to 223. Class D, that first octet will be 224 to 239. And this is actually a special class that is only designated for multicast addressing. So if you're sending a multicast stream, you work for Netflix and you're streaming, and your streaming server has a multicast address, it will be 224 to 239, the first octet. And then we have class E, which is reserved for experimental purposes and is not used in the standard internet options. That first octet will be 240 to 255. Alrighty, let's go ahead and do our quiz. And then we'll take another break. So my voice definitely needs it, and I'm sure you guys are like, well, what the fuck? My brain is fried. Okay. Domain 1.7. No quiz? Come on. Let me see my lessons. Oh, I guess we don't have a quiz here. Okay, that's fine. Maybe I got disabled on accident. I don't know. No quiz. That's fine though. So let's go ahead and take another 10-minute break. Let's come back. I got 7:02 on my time, so I'm gonna put the timer for 10 minutes, and we'll probably come back at 7:13. Okay, let's go ahead and jump back into it. So I know that IP addressing section was a little long, but now we're going to jump into domain 1.8, which is going over modern network environments. Now, these are technologies we're about to cover that, I mean, we could spend like a whole week diving deep into these topics that we just don't have the time to. Because remember, Network Plus, we're just glossing over, high-level overview. We're here to pass a certification exam. But I'll go over with you as best as I can to at least have these technologies make sense. So we're going to start off going over SD-WAN, VXLAN, and Zero Trust architecture. I think in this section, do we go over SASE or SA? Nope, we don't. So first, let's talk about software-defined networking. So software-defined networking, or SD-WAN, which originally was like a subset of SDN, but now they're kind of making it its own thing, which I'm totally fine with because SDN kind of refers to like data center, campus, enterprise, whereas SD-WAN is exactly how it says. It's the WAN. It's your connections out to the internet. So SDN is a modern approach that gives you a single pane of glass, a centralized controlled view of your enterprise that allows you to programmatically and automate the configuration, the upgrades, the policy, and overall management of your network. It does this by abstracting the control plane into a centralized place where you manage it as a centralized server, which really just means you getting into a GUI and control and, doing your configuration there. Your data plane will stay at that network device, and then you, as the network engineer, control that GUI to set policy to configure your network. So instead of you being in the CLI to push a change to 100 devices, you go to your control plane or your controller and you make that change. SDN is also what cloud networking is. So when you have seen me in the past deploy a VNet in the Azure portal, that's software-defined networking. I'm not going into some sort of Cisco router, Juniper router, CLI and configuring it. I'm managing everything from that portal, okay? So to read this definition, software-defined networking is an approach to networking that uses software-based controllers or APIs to communicate with underlying hardware, infrastructure, and direct traffic on the network. So in this diagram I have up here, what you see here is that centralized control plane, the data plane still at these routers, and we're split here between northbound interfaces and southbound interfaces. And at my computer here, I'm communicating through this with northbound interfaces, which really just means that I maybe have set up a REST API to this controller that says, hey, get me the interface brief command from all my routers in my, down here in my fabric is what I'd call this, my fabric. So that controller says, cool, I got your REST GET message. I'm now going to send a southbound API request to these devices, which could be like RESTconf, like a RESTconf message or a netconf message. And then that device and all the devices will respond back up to my controller. And then my controller will send an information that I requested back here in some sort of JSON or structured data format. And then I'll reformat that data how I like. And that's software-defined networking when it comes to using APIs and programmability. Beyond that, we have things like Cisco SD Access. I'm a Cisco guy, so that's what I know. Like Cisco Catalyst Center and SD Access that also do SDN, and that's just a control. It's a GUI, right? I don't really have time to get into the DevNet sandbox of Cisco, but yeah, we won't show you. Okay, SD-WAN, another software-defined technology, but this is for the WAN. So this is when we have multiple customer edge devices facing our ISPs that we manage from a centralized place, like our vManage node here. This is Cisco SD-WAN again, right? Just as what I know. So that's how I explain it best. That's controlling how these edge devices or routers send traffic out to the internet. So our transport layer here, our transport connections is really agnostic when it comes to SD-WAN. This router could have a connection to an MPLS connection out to an ISP. It could be connected to a Starlink, and it can have a connection to a 5G hotspot. And my SD-WAN is controlling that traffic flow out all three forms of that transport, okay? So, some more kind of definitions here that are going to be good for our exam. What does it provide us? So it gives us application awareness. So with SDN and SD-WAN, we can prioritize traffic based on the application. And that's something, again, we configure. So in our SDN appliance or our SD-WAN appliance, we can say, hey, I'm controlling this edge router via vManage. And I'm telling this edge router that Microsoft Teams is something that's business critical. So you're going to go out your MPLS connection. But anytime a user wants to go out to YouTube, you're going to come out your 5G connection here. So I am aware of the applications that users are trying to reach, and I'm going to direct traffic how I see fit based on the priority I want to set based off multiple different factors, bandwidth, latency, whatever the case may be. So it's transport agnostic, but it's also application aware. And we can do this in the campus as well. So like our Catalyst Center, Cisco Catalyst Center can do this for your campus networks, not just across the WAN, but within the LAN as well. Be aware of the applications users are trying to use. Maybe it's like an on-prem service, right? And you can direct it that way. We also get zero-touch provisioning. So this is a feature that allows for automatic configuration deployment of network devices without manual intervention. Really what we're saying here is, okay, so I have Cisco Catalyst Center. I have SD access set up. And I need to add 4 more access switches. All I do is power on that access switch, give it an IP address, and then without going in the CLI of 4 of those switches and putting my base config and doing configuration, they will connect. They'll become part of the fabric. They'll connect to my Catalyst Center, and from there, I manage them. So it's zero-touch provisioning, right? Or maybe I have a baseline config that'll get assigned to it right away. It touches our network. I see it come up. I push a golden configuration baseline config there, and then I go and make any little minor changes and tweaks I may need to. Again, and then SD-WAN, it's transport agnostic, like I've already said. And then with SDN and SD-WAN, it's central policy. So when I need to update a routing policy, I need to manage security policies, whatever the case may be, I need to gather telemetry. It's all from a central place, from a centralized control plane. Marketing says a single pane of glass, but it's true, right? How do I show you? So I use Ubiquiti for my home office, for my home and my actual business office, and that's SDN. I'm hesitant to go on there just because I'm like, I got public IPs and stuff on there, but we can log in. It's fine. So I have my Dream Machine Pro here, and if I wanted more sites, meaning I have more offices I want to manage, and I have Ubiquiti routers there, what they call like their cloud consoles or whatever, right? I can manage them all from this centralized plane, okay? So I can come in here, manage my access points, manage my router. I can look at my client devices that are connected. It gives me a topology here. What's missing in here is I have a Cisco Catalyst switch that it doesn't really recognize this topology. Like you see, it's just like this floating access point. That's because it's connected to a Cisco Catalyst switch, but you can get telemetry from here. So I can go on this even GVM, and I can see its traffic activity, right? I can do that for my iPhone, but I don't want to show you guys all my traffic activity. But yeah, so that is a form of SDN. And there's also like, well, anyways, that's a form of SDN, right? I can control an entire enterprise from this one console here. If I had all Ubiquiti switches, all Ubiquiti routers, I could do that, right? Okay, next let's talk about VXLAN. So this is a technology that enables data centers to operate within the same local area network, even if they're geographically dispersed. That's right. So when we enable VXLAN on our geographically dispersed data centers, we could do stuff like VM motion, where I move a VM off a host in my data center in Phoenix, and I can VM motion it over to another host in my ESXi cluster over in New York through this VXLAN tunnel that shares a local subnet. So with VXLAN, it enables us to extend our layer 2 broadcast domain between data centers or sites that are geographically dispersed. That is in totality what VXLAN does. So we can have the same VLAN numbers and tags and subnets on these servers that sit in completely geographically different locations, and it doesn't matter what our transport network is. All we need is that these VTEP 1 and 2s to make a tunnel, a connection between each other, and then our data centers believe that these servers and these servers are in the same LAN, sending broadcast messages to each other. So Not going to dive deep into it. You can see the packet here of VXLAN. You have your original, a VXLAN header, a UDP header, an outer IP. Like, so this is like our kind of like our tunneling. It's getting tunneled, right? And then our MAC header, okay? We have a other technology we can talk about here, the data center interconnect. That's what VXLAN does. So it's used to connect different data centers, called data center interconnect. And it does, VXLAN uses layer 2 encapsulation, which allows the creation of a virtual layer 2 network that can span over a layer 3 infrastructure. Real talk, people, like real human talk. Data center in New York, data center in Phoenix, they think they're on the same LAN. It's great. And you get a lot of capability from that. Okay, zero trust architecture. Another thing that I have a 50-minute video on that I'm going to try to explain in a couple minutes. Zero trust architecture. It's not a single device that someone markets to you that says, you get zero trust now. What zero trust architecture is really a way, it's a policy and a way to design your enterprise for the tightest security possible. So with zero trust, we have three main tenets. That is the never trust, always verify. That's always assume breach, and the principle of least privilege. Now, how we accomplish those three basic zero trust tenets is up to you, the administrators, but that's what it is. It's really just a policy. It's a cybersecurity framework that says, here's how to have the best protections on your enterprise. In our modern enterprises where we have resources in the cloud, we have remote users sitting at their home, and we still have our on-prem data centers. If we follow a zero trust architecture, we're going to structure our enterprises in a way to follow those three basic tenets. Always assume breach, so continuous monitoring of all of our infrastructure in a proactive approach. This can be done using like EDR, XDR technologies, IDS, IPS, SIEM, large learning models that create user baselines. All those combined, goes into the principle of always assume breach, continuous monitoring. We have never trust, always verify. So what we're saying there is that when a subject, which could be a user, could be a service account, could be a computer, needs to access an object that belongs to our enterprise, never trust, always verify. Even if they've been verified before, they're going to have to re-verify again to access our enterprise object or resource, which could be as simple as accessing a SharePoint portal from your house, and the SharePoint portal sits on the data center on-prem, but you're always going to have to re-verify. This can include username and password, certificate, any form of credentials. This could be enforcing multi-factor authentication. This could be having some kind of contextual awareness on our subjects trying to access resources. So how we do that, again, could be like Microsoft Entra ID and Intune. It could be Microsoft Active Directory. It could be a CASB appliance, which when we're trying to access our cloud resources, that's doing that continuous monitoring and that verification, okay? And then the principle of least privilege. When we're doing identity access management, making sure we're assigning permissions and privileges to exactly what that user needs. This falls into RBAC, role-based access control, okay? So all that is zero trust architecture. You can see here some of this actual names that zero trust architecture uses, and this is straight from the NIST zero trust framework. This is kind of like, not to say invented it, but this is what you read. You want to learn zero trust architecture and not just get sold something by a cybersecurity vendor that says it does it for you. Read this framework and then adjust what you currently have to fit that. But they say zero trust architecture essentially works like this. You have a control plane which you configure as an administrator with a policy engine and a policy admin here. And that creates what's called a policy decision point, a PDP. So policy engine, let's say that's Cisco ISE, Identity Services Engine. That's Active Directory. That's Microsoft Entra ID. And then you're the policy administrator configuring, that principle of least privilege, making sure you're always verifying subjects trying to access network objects. And then you push those subjects through a policy enforcement point. Now, again, that's also, like when I'm trying to access the network, maybe that policy enforcement point is Cisco ISE, right? And yeah, that's how they kind of design it, okay? It's hard, trying to go through all this. Let's move on. Okay, let's do our quiz. It's hard not to dive deep into stuff like that, right? It's like, man, VXLAN, SD-WAN, SDN, that's all like, you know, why can't I don't know what's going on with my quizzes. Oh, there we go. Okay. So domain 1.8.1. It's hard not to dive deep into that stuff. As you guys can tell, it's like, man, I want to keep going, but it's just Network Plus. Okay, let's do our quiz. 1 second. Let me bring up something on my other screen here that you guys can't see. Okay. So in the context of SDN and SD-WAN, what does application aware mean? So we're going to go with B here. The network prioritizes traffic based on the type of application to ensure optimal performance. So yeah, that's like, it's aware. It's aware of the applications users are trying to access, and we're going to put priorities on that. So the answer is B. Question 2. What is the main purpose of virtual extensible local area network in data center environments? Remember, VXLAN gives us the ability to take geographically dispersed data centers and make them believe they're part of the same broadcast domain, the same layer 2 domain or switched network, which gives us a lot of capability. It does not increase the number of routers. It doesn't replace layer, well, no, it doesn't replace. It has nothing to do with cabling. So we're going to go with D here. To address scalability issues associated with traditional VLANs by extending layer 2 networks over layer 3 networks. Question 3. Which of the following is a key characteristic of software-defined wide area networks? It's not limited to just an MPLS, physical. So it actually, obviously, we need a router for SD-WAN to work, but this could be like a CSR router that's virtualized. Like you could use a VM to do SD-WAN with your router. So this one I'm not going to go, it's A, right? It's transport agnostic. I said it like 5 times, so we know that. It can use any form of transport. Question 4. Which principle is not a core component of zero trust architecture? Another easy one. A. What's our core tenet? It's never trust, always verify. So A is not a core component. And again, if you want to look at that NIST Zero Trust Architecture, I think it's 800-207. This, I mean, if you go read this, if you're a cybersecurity professional, or I know there's Network Plus, but like if you want to go be like, I know Zero Trust like the back of my hand, and you go to an interview and you read this, you read some of these other NIST frameworks, like you're pretty good, right? That's the holy Bible of Zero Trust. Okay, question 5. Which of the following best describes software-defined networking? No, not physical. Hardware-based controllers, not necessarily. Right? It can be like Cisco Catalyst Center could be a physical server, but you could also virtualize it. A networking model that uses software-based controllers to manage and automate network traffic. That's our answer right there. So, which of the following best describes software-defined networking? We're going to go with C. A networking model that uses software-based controllers to manage and automate network traffic. Question 6. What is the primary benefit of zero trust provisioning in SD-WAN? It requires manual configuration. I don't think so. So we're going to go with B. It doesn't limit scalability. It doesn't increase the need for on-site network admins. You know what? It's funny because, like, does it decrease, though? I mean, you still need someone to rack and stack, like, you know. But anyways, B. It automatically configures and deploys network devices without manual intervention. All right, awesome. That is 100%. We're going to take a quick 7-minute break. I need to rest my voice. I was getting a little bit too animated there. We'll come back at 7:40 East Coast time, and then we'll finish up Domain 1, okay? All right, guys, let's go ahead and jump back into it. So now we're going to finally finish up Domain 1 of Network Plus. And remember, this Domain 1 is kind of like the longest, so it is what it is. So finishing up our modern network environments, now we're going to go over SASE, or SASE, and SSE, and infrastructure as code. And also IPv6, which, yeah, we'll go over IPv6 as well. So SASE, SSE, I kind of look at this as another like SDN offering, but it does a lot more. So SASE, Secure Access Service Edge, and Security Service Edge, these are architectures. Yes, they're products that now vendors will sell, but they're products that wrap up a lot of features, technologies, security, and software-defined capabilities onto one package. So with SASE, this is going to provide a holistic approach to secure network access by combining SD-WAN with other security functions. So with SASE, we're pretty much getting that SD-WAN functionality. Remember, this is kind of operating at our demarcation point, right? It's operating at the border of our network, where we're getting the SD-WAN functionality, but then we're also going to get a lot of other security functionalities as well. Stuff like secure web gateways, which think of that as like, it's kind of like a firewall, but it does a lot more. It's application aware. It does URL filtering. It does kind of like some proxying for you as well if you have it configured that way. Inspecting packets. Then we have things like CASB, Cloud Access Security Brokers, which is going to kind of be like resources. CASB can monitor that. They can apply policy, so they can enforce policies and permissions on your users accessing your cloud resources, especially if you're in a multi-vendor cloud environment. And it also gives us zero trust network access. Now, architecture, remember, architecture is like, it's a whole policy, it's a whole framework, zero trust architecture. We're talking zero trust network access. So it could also be that policy decision point and that enforcement point for your users coming in. And that's what it can provide us. It can provide us that authentication and authorization functions. Where SSE, that's just security. So SSE, you lose the SD-WAN functionality. So all that routing, all that automation you get with the networking and the routing policies specifically. And SSE is just, this is a security umbrella for you. This is an all-in-one security appliance for you that does a lot, right? Okay, so some things that it gives you that we're just going to have to, this is what on the objectives, these notes, so we're going to go over them. Unified security and networking. So SASE and SSE provide a unified framework for managing both networking and security, reducing the complexity and cost of deploying multiple standalone solutions. So remember, this is an enterprise solution. So this will incorporate your spokes, your main campus. Scalability. By leveraging cloud-native architecture, SASE and SSE can scale up and down to meet the needs of dynamic workloads. So remember, this is not a physical hardware appliance. This is like something that you can deploy in the cloud. It's a software that you can deploy. And with that, you can scale it up, scale it down. You get that elasticity. Improve performance. So since SASE utilizes SD-WAN to optimize traffic routing based on real-time conditions, we also have that like right of bang routing where it's like, oh, all of a sudden when our pipe's getting full, start doing some QoS, start prioritizing traffic, right? So we, based off real-time conditions. And then we also get that zero trust model. So we get that zero trust network access integrated into this. Okay, I'm trying to not be long-winded. Next, we're going to talk about infrastructure as code. So this is a key concept in modern network environments that allows for the automation of infrastructure management. So let's take a pause there, take a breath, okay? So with traditional networking, when I need to go make a change on a router, I go into the CLI, I make the change, I save it, and then I back out of it. With automation is the ability from your development environment, whatever that may be. Maybe it's just a local computer. Maybe it's a jump box with Linux jump box where all the network engineers run scripts from. Maybe it's something like Ansible Tower. Maybe it's something paid for like Cisco SD Access or Catalyst Center, and you automate that way. Whatever the case may be, right? It's the ability to make changes, do upgrades to multiple nodes all at the same time. That's just automation. Now, when we get into the operations of that, getting it to a more enterprise function, looking at our enterprise, looking at our network infrastructure to include our cloud-based resources, our on-prem resources, and even our servers, we start talking about something called infrastructure as code. Where we look at the infrastructure not as individual devices, but now we look at it as a single code base. Where maybe I have, IPAM through NatoBot, I have my source control management through GitHub, and that is how I look at my network now, as a single piece of code, a master repo that I make changes to and apply those changes from that master repo. And there's multiple technologies to make this happen, okay? That's what we call infrastructure as code. So infrastructure as code is automation, but for the at the actual enterprise level is the way I look at it, where we start building pipelines, where we start integrating multiple developers into our pipeline to create the code that manages our entire infrastructure, okay? So with Network Plus, they say we got to learn some terms here: playbooks, templates, and reusable tasks. So playbooks and templates are predefined sets of configuration and tasks that can be reused across multiple deployments. Think of this like as a golden configuration, a baseline that we push out using Ansible. We put that baseline, we deploy Ansible Tower, and that gives us a web GUI where you hit a little rocket, and that sends that golden baseline out to every device. That's a template. That's a playbook. That's a reusable thing, a standard way to configure infrastructure. So yeah, example, Ansible playbook, okay? Upgrades. So infrastructure as code allows us to do upgrades all at once. So if we talk about infrastructure upgrades, maybe we use something like Terraform, where we have multi-vendor cloud environments and VPCs and VNets and NAT gateways and storage accounts and Google, storage buckets, S3 buckets that we have to manage and upgrade. And we do this quarterly. Well, we can use Terraform as our application or code of choice to actually go do those upgrades. And then dynamic inventories. Dynamic inventories are a list of infrastructure components that automatically update based on the current state of the environment. So imagine I have that Terraform or that Ansible playbook that's managing, configuring, and upgrading my infrastructure, but I need to know the IP addresses of that infrastructure. So maybe I have an inventory where I query my IP address management system like NatoBot that says, hey, query NatoBot, make sure we're getting the most up-to-date IP addressing, and plug that into this playbook. That's a dynamic inventory, something that we request each time we run our script. Now, I have this diagram up here where we have a pipeline. This is what we call like Git operations, or our continuous integration, continuous deployment pipeline, where we have our developers, we have our code, we have our source control. We're going to have a lot of other technologies in here like Jenkins, like Jira, like content management databases like Confluence. Whatever the case may be, we have a pipeline to develop our code, stage it and test it, and then put it into production. So getting into that, one of the main softwares, one of the main technologies you got to use is Git. So part of that pipeline is something called Git operations, a Git workflow, which gives us version control, which gives us a primary repo for our production. And if we want to make changes, we branch off that repo, make our changes in a local environment, stage those changes, have senior network engineers or senior DevOps engineers look over our changes in our code. We could do something like A/B testing, blue-green testing, where we send the script to a sandbox environment. Did it work? Okay, now we'll complete that pull or merge request and put it into the central repository, our main branch, our master branch, okay? All right, now, it's hard. IPv6 addressing. Another thing that they just put at the end of this, called it modern networks, but IPv6 has been being taught forever. When I started teaching networking, I wasn't going over, Catalyst Center, but I was going over IPv6. So why they put it in this section, I don't know. That's CompTIA. But IPv6 is another internet protocol that was invented because IPv4 is being exhausted. So IPv6 is a 128-bit address that's represented in hexadecimal, not dotted decimal, hexadecimal. It's 128 bits, represented in hexadecimal, and it has 8 hextets. With IPv6, we don't have the need for private versus public IPv6 addresses because there's so many that every IPv6 address that you assign to a node on your network, router, switch, computers, printers, whatever, can all be a public IP. We don't call it that, but they can all be unique without the need for private addressing. Okay, some of the IPv6 technologies they want you to know about. Yeah, we're not diving deep because, again, on the exam objectives, it's just like you need a quick overview. IPv6 is represented in hexadecimal. There's no public or private IPs. And that's pretty much what we need to know about it. It's 128 bits, okay? Represented in hexadecimal. Now, when it comes to running IPv6 and IPv4, there is some technology we're going to talk about. So tunneling. So tunneling allows us to tunneling allows IPv6 packets to be encapsulated within IPv4. So yes, you heard that right. We could have an IPv4 connection out to an ISP, and we could have IPv6 enabled devices here that get tunneled through that IPv4 packet and reach the other end and then talk to our other IPv6 enabled device here. This is how we transition to IPv6. It's a transition strategy. We also have dual stack routing, where we have IPv4 and IPv6 routing at the same time. A lot of times, like at your house, depending on what ISP, where you're out in the country, they do that, dual routing, where a router is configured for dual stack operations, where they have a routing table for both IPv4 and IPv6. Then we have NAT64. This is a translation mechanism that allows IPv6 only devices to communicate with IPv4. So if we have an IPv6 enabled device only that needs to talk to IPv4, we could implement NAT64 to do that, which is achieved by translating IPv6 addresses into IPv4 addresses and vice versa. So just doing that translation. All right, let's do our quiz. So this is domain 1.8.2. Let's go to our quizzes. Too zoomed in here. Okay. Domain.1.8. And let's start this quiz. Okay, question 1. What is config... Oh, something I didn't talk about. So cool. I'm glad we did this. We're doing this question. What is configuration drift, and how does infrastructure as code help prevent it? So what configuration drift is, let me explain it real quick. So imagine we're like deploying, multiple switches across a vast enterprise. So this is like maybe our HQ. We have all these access switches. And then we open up a spoke office. And we got some unique things in the spoke office. Maybe we have like NAS attached here. And just extra things, right? So we try to have a baseline for everything. But we have this unique thing where we have a trunk port to this access point here, which we don't have here. This is all access ports to our access points. But we need a trunk right here so we can do something like Flex Connect, okay? It's a wireless technology. So this is a trunk. My handwriting's so bad. I'm going to get roasted. Trunk. So this is a trunk here. So typically our access switches will only have trunks connected to other switches. That's at our HQ. But then right here at our spoke, we have a trunk right here. So we have all these unique things happening at the spoke that maybe we're like, hey, we don't want. Let's find a different solution because I want all my switches on the same exact baseline. Like the DoD environment, if you have every single switch and you tell your ISSO, your cybersecurity office, every single switch has the same baseline, when we go and do our compliance checks, they will just check one switch and be like, well, every other switch is like this, so we only have to check one switch, right? So that's like easy. So maybe there's a reason why we don't want this configuration change. And we call that configuration drift. Pretty much just over time, little changes here or there happen where our baseline is no longer set on all of our devices, right? So that is what we call configuration drift. So now, what's the answer here? So, what is configuration drift and how does infrastructure as code help prevent it? So we're going to go with B here. Configuration drift refers to the divergence of infrastructure from its intended state. Infrastructure as code helps prevent it by automating compliance with predefined configurations. I always think of that just like our baseline, our golden config, right? All right, question 2. What is the main advantage of using version control in the context of infrastructure as code? So version control, I should have defined that a little bit more. So for instance, in software development, this is something you learn like Computer Science 101. Let's just look at my MacBook here. You see this version? I'm using 15.2. So that's like my major version, my minor revision or version, and this would be like my, what's it called? Major, minor, and patch, right? And then we could also have beta right there, like beta. So version control helps us track our changes, essentially. Like, hey, when we upgraded to version 1, like in GitHub, we could put this. When we upgraded to version 1 in a little help me or like in Markdown, we upgraded to version 1, this is all the bugs we fixed. So then let's say you go to version 1.2 and then 1.3. And you can see in each version things you fixed. And if that new version created a new bug, you can roll back to the other version. That's what version control allows us to do. It just allows us to track, right? So I have the same answer twice here. I need to take note and fix that. Okay, I'll make note of that. But yeah, it's A or D here. I'll go fix that. If you bought our course, yeah, I'll fix that. But it helps in keeping track of changes and rolling back problematic updates. That's what version control helps with. Let me just, for a second, take note of that question. Hold on. See, people have commented, I thought I fixed this already. Duplicate answers. Okay, that is my bad. All right, question 3. Which of the following is a key benefit of using Secure Access Service Edge? Remember, Secure Access Service Edge is kind of like that all-in-one umbrella that does security for you, a lot of security functions, and also SD-WAN. So, and it's also cloud native. What we mean by that is it's virtual. It sits in the cloud. It's not a physical hardware appliance that we have to go buy. So it centralizes network security and improves access performance by leveraging cloud native architecture. That is one of the key benefits. One of. There's other things, right, that it does. Okay, question 4. Which of the following strategies is used to ensure compatibility between IPv4 and IPv6? So that's dual stack, right? The rest of these are nothing to do with IPv6, IPv4, like transitions or anything like that. It's kind of like a little give me there. But yeah, dual stack. That's when a router or device, firewall, whatever the case, your routing device runs IPv6 and IPv4 at the same time. All right, question 5. Which of the following best describes infrastructure as code? So not manually. I want to go with C here. A practice that uses code to automate the management and provisioning of infrastructure. Okay. This is the only, we're not going to get 100 because that duplicates mess up my scores. All right, question 6. What is the primary purpose of Secure Access Service Edge? Primary purpose. So that's to unify. You know, it's a single appliance. If you've taken Sec Plus like back in the day, we used to call this UTM, Unified Threat Management. But this is different, right? This is cloud. This is our modern day stuff, evolving networks. But that did the same thing. So it's just funny how as technology changes, our concepts don't change. We also want another way to unify all these different features and functions we had to simplify our work, right? But yeah, B, to unify network security and wide area networking in a single cloud delivered service. And I missed one, even though it's duplicate. That's okay. All right. So we've been going for about 3 hours, guys. I know I'm taking a lot of breaks. It's just to save my voice. I'm going to put 15 minutes on the clock because I want a little rest before we jump into the next domain. But yeah, after 15 minutes, come back at 8:15 East Coast time, and we'll get into domain 2, which is only 4 subsections, domain 2.1 through 2.4. I think first is switching, routing, wireless, and then the last one's like physical infrastructure. So put 15 minutes on the board.